Hello and welcome back. In this video we'll look at another example of explainable AI. In particular we focus on ShapleyValues, where we use the wine quality dataset in regression mode that we have already covered in a separate exercise. So we won't discuss the exploratory data analysis or model considerations here. We use the same models, and the ShapleyValues have the advantage that we can also use it with the black box model. That means we'll focus on how to make predictions explainable post hoc after we have made them, in particular with the black box model. The ShapleyValues originate from game theory, and we can use them to analyze how much a given feature contributes to prediction. In a sort of high-level and crude way, we could interpret the features in the machine learning model as a player that work together in a team, and this team achieves an outcome. In our case, the outcome is the prediction. With the common analogy we can draw is that, say, the team is playing a football game, and each of the player has different strengths. Just in a real football game, you would have people that are good at maybe attacking or playing, shooting towards the goal. Other players are good at defense, and so on. In a similar way, we can interpret the team as the prediction method or the prediction itself, and then the features are team players, and they sort of work together to make this prediction possible and achieve an outcome. So we import our standard libraries, we take the random forest regressor, and here we import the Shapley value package as well. We download the data as we've done before and split it into test and training set, make our predictions with the same model that we have also used elsewhere, and append this to the data frame. First, we look at the global interpretation. Previously, we can also have looked at the correlation matrix between the variables in the data frame, and now we use the model and ask the model, so to speak, which of these variables are the most important ones. So we use from the SAP tree explainer because we had a random forest regressor, and ask for the Shapley values on the training dataset. And then this package provides a nice convenience function to do a plot of those. And unsurprisingly, those variables which are most highly correlated with the target variables have also the most predictive power, and they are also the most important ones for our regressor. We can also look at this in slightly more detail when we use the summary plot of the Shapley values. Here we sort of color code the same thing. We have still the same order, and now the blue dots correspond to a low value of the feature, and a high dot corresponds to the red color corresponds to a high value of the feature. So we can see that, for example, for the alcohol content, the impact is concentrated on the negative side of the Shapley value, so it pulls in one direction for the low values of the feature, and as we move towards the high values of the feature, this pulls it into the other direction. And the sulfates go the other way, go in the same way, and the acidity goes in the other way. And the other features you can see here, they are more centered on zero, so they contribute a lot less. Only in some specific values they sort of pull the model prediction in one direction. But you can see in particular those features here, they have very little impact. So these are, shall we say, the least important team players in our prediction team. Now we look at dependency plots. These are scatter plots that allow us to explore how a single feature contributes to the prediction in more detail. Each point in the scatter plot is a single prediction, and on the x-axis we have the variable with the numerical values, and then on the y-axis we have the Shapley value, right? And so we can see that as we move to higher values, the Shapley value almost linearly increases, right? It's a slightly different representation of this one. Here we see more like a summary of where these values are, and here we can have a more detailed understanding of how the behavior is. You can also add a second variable to it. This is then color coded here, so we can, for example, explore how two of these features behave together. Next, we can look at all the interactions between these features. And we can use this interaction plot on the diagonal. This is what we had before. It's now, of course, slightly distorted because of the aspect ratio. But if you, for example, look at the alcohol sulfates and we scroll back up again, you can see that this behavior is exactly from this, just as a different aspect ratio. And now we can, for example, look at how the Shapley values behave if we have the team of alcohol versus sulfates or alcohol versus volatile acidity and so on and so forth. So we get an insight of how the combination of different team players interact with the predictions. But more importantly, we can also create a local interpretation from our black box model. So the way this works in the Shapley approach is that we look at the computed base value. This is like the mean prediction across all the training data. So this is what the model sees during the training, and the prediction for the current sample is then denoted by f of x, and we can interpret this in the following way. The predictions are split into the average, this is the base value, plus a deviation that originates from the values and feature specific of these features. So this is where the sort of team comes in. We can say that across all of the training data, we have this base value, right? And then for each prediction, this base value gets modified according to what the team of features does. So we can express this as pseudocode. The prediction is the model prediction, right? So this is what we have. And the prediction mean is the mean of all of these predictions. And then we create a Shapley factor for a specific event, which is essentially the sum of all these Shapley interactions for the specific event. And then the specific prediction is the mean prediction plus the way the Shapley factor modifies this. And this allows us to interpret how for each particular instance of the data we want to analyze, the various features modify the outcome. So we do this here. We get the predicted data, we get the mean prediction, and then for the index 0, in this case, we get the interaction between all those features, right? So the model prediction is this one, and as we said before, the mean prediction and the interaction is this one. Notice here that we use the training data itself, right? This is because the training data is all that the model sees. So we normally would, of course, use the test data, but here we want to analyze the interaction between the features. So in order to avoid any numerical shifts, because maybe the training data and the test data, they're finite data sets, and to be able to reproduce these numbers exactly, not approximately, we use the training data here. But of course, in a real situation, we would rather use the predictions from the test data or from the new data set. We can also visualize this for the specific sample. The SI package provides a convenience function for this. It's based on JavaScript, so we need to initialize it here, and then we use the force plot method. So we have then the value, and again here we see how the different features either push the prediction to higher values or lower values. Right, the alcohol, as we've seen, is the most important contributor. This is why, for example, here we have the largest fraction of it in the sulfates. It was the second most important variable, but this goes the other way around. And if we go back to our variables here, alcohol and sulfates were indeed the most two important variables, and their interaction then defines, as we can see here in this graph, how each individual prediction is pushed to the specific value based on the values of the specific features for the specific event.